What is the exact temperature of a satellite flying in the cosmic void? The only way heat is transferred in the space is exactly through radiation. The satellite receives energy from the sun and heats up as a result. However, it also radiates energy and cools down because of this. The established temperature corresponds to the equality of these two energies. If the entire sky shone like the sun, an object inside such an enclosed sphere would have the temperature of the sun. But the sun, when we actually look at it from a satellite orbiting the Earth, really occupies only 1/200,000th of the entire celestial sphere. Therefore, the satellite's temperature must ensure the radiation per unit area is 200,000 times weaker than the sun's radiation. But according to the Stefan Boltzmann law, the thermal radiation from the surface area of a body is proportional to the fourth power of its absolute temperature. The surface temperature of the sun is approximately 5,800 degrees Kelvin. Therefore, to establish thermal balance, the temperature of the satellite must be less than the temperature of the sun by the fourth root of 200,000, which is 21 times. We divide 5,800 by 21 and get 276 degrees Kelvin. This is a good estimate. The Earth is a satellite of the sun, with an average surface temperature of 287 degrees Kelvin, slightly higher than 276 due to the greenhouse effect. To carefully observe how thermal equilibrium is carefully established in a vacuum, we carefully visited the molecular laboratory at Novosibirsk State University. Inside the vacuum chamber, 2 copper plates are carefully suspended. The surface of the left plate is polished on both sides, the back side of the right plate is polished, and the front is blackened. The temperature of each plate is measured using a separate thermocouple. We will illuminate the plates with a powerful halogen lamp, which in our experiment will play the role of the sun. Within a few minutes, the temperature of the polished plate increased from 24 to 41 degrees Celsius, while the temperature of the blackened plate rose to 105 degrees. But the plates not only radiate heat, they also transfer it to the surrounding air. To completely eliminate this influence, we will close the chamber and pump out the air slightly. The pressure in the chamber is currently about 100,000 times less than atmospheric pressure. We illuminated the plates with a lamp. Then the blackened plate heated up to 215 degrees Celsius, while the polished one reached 98 degrees Celsius and was still slowly heating up. Suppose that out of approximately 100 units of incoming energy, a mirror-like plate reflects 90 units and absorbs 10. Then, when thermal equilibrium is established, each side radiates approximately 5 units of energy. Let's also assume that the blackened plate absorbs 90 units and reflects 10. How are these 90 units radiated? The blackened side not only absorbs but also radiates 9 times more energy than the mirrored side. So it will radiate 81 units of energy, and the mirror side will account for 9 units. Look, in the second plate, the mirrored side actually radiates 1.8 times more than in the first one. Therefore, according to the Stefan Boltzmann law, the absolute temperature of the second plate should be the fourth root of 1.8, which is 1.16 times greater than that of the first plate. It turns out by rotating the satellite to face the sun with either its blackened or mirrored side, we can regulate its temperature within certain limits. What would happen if 2 satellites were sent into space, one with a completely mirrored surface and the other with a completely blackened surface? Which of these satellites will have a higher temperature? Please, kindly share your thoughts in the comments on our YouTube video.